As you can see, we have a kind of an interesting score distribution here, where it seems like the greatest number of students in the class did very well, and then a few down here didn't do so well. Consequently, that brings the average way down for everyone. The average score was a 68.6. Median score was a 75.5. When there's a huge difference between the median and the average, that indicates that there's a fair number of very low performers on here. I've talked with some of you already, or some have come and talked with me. If you are in a position where you would like to discuss your status in this course, you're always welcome to do so at any time. My advice usually, though, doesn't vary a whole lot. The biggest advice comes down to practice. Doesn't matter how good you are or how not good you are to begin with. The way that you get better is to practice. And I don't know if any of you, I know if I were to start listing a bunch of things like sports or music or art or whatever, you don't, even if those are hobbies or interests to you, those skills don't get better unless you practice. And some people just happen to be naturally more gifted in some things than others. And whether that's fair or not, that is a reality. I'm not going to be a professional basketball player. I tried playing basketball for years, and I realized that I can only make a fool of myself so much, and then it ain't fun anymore. Okay? Unfortunately, you signed up for this class. So you don't want to make a fool of yourself, or you don't want to not do so well. So the way that you're going to do better is to simply practice. And for some people, it means you've got to practice more than others. And if you look at your star athletes, your star athletes are not only the ones that are the most talented, but they're usually the ones that also practice the most. They're the ones that are outside of the designated practice time practicing the most. So even those of you that already do well, you can probably do better simply by practicing more. And so that's my little spiel. I feel all right with where the test is at because, again, the largest number of students in this class did very well. If you didn't do so well, again, my suggestion would be to practice. I can go through the Master in Chemistry and just see a whole bunch of holes. And I know things come up. You don't have time. You got jobs. You got family. You got all sorts of other things. But I can't simply promote you on to the next class or whatever simply because I think you're a good person or I like you or anything. It has nothing to do with whether I like you or whether you're a good person or not. It ultimately winds up being how well you perform at the end. So, all right. So that said, if you look at the test, somebody asked what is the +3 on there. When I see a large disparity between the average and the median that I don't like, and nobody scored perfect on the exam, I often add a few points to that score to bring it up a little bit higher, but I'll never bring it up any higher than a 100%. So the highest person without the 3-point adjustment was a 97, and after the 3-point adjustment brought the highest score up to a 100. So any questions? Any questions? All right, so today let's just do a quick check-in as to where we are and where we're heading. I like to pull out the syllabus and do just a very quick check of where we're at this point. Exam 3 covers gases and thermochemistry. Now, there's an upside and a downside to this. If you're coming into this course with a background in high school chemistry, it turns out that not a whole lot of high school chemistry classes cover one or both of them. And so for many of you in here, you're going to be in the same boat. You're going to be learning this stuff new and seeing it new for the first time with everybody else. There's a few of you, depending upon, again, your high school and the background, you maybe have seen one or both before, but many haven't, and so for many, these are new things. That said, some of the stuff that we've used before, like the mole concept, doesn't go away. If you've looked ahead at all to problems in here, you'll see that each one of them does use the mole concept somewhat. And so if the mole concept was something you were or are still struggling on, I would very highly recommend that you go back and review stuff here in chapters 3 and 4. As far as when our next exam is scheduled, next exam is scheduled for Thursday, November 2nd. And again, that'll cover chapters 5 and 6. Labs between now and then. I do realize that I won't be teaching you in the lab, but you'll be doing a lab on gas laws, and then you'll be introducing thermochemistry and the project intro. And have you talked about projects? I thought I heard Professor Creel the other day talk about projects a bit. Was he?
A little bit.
A little bit? Kind of intro? Okay. So you'll have a little bit of an intro to it then, and then you'll be doing like a 3 or 4 week project and doing some project presentations in lab as a part of your lab activities. So, any questions of where we are or where we're headed? All right. Coming into class here today, there were 3 balloons sitting right here. And if you've not had a chance to answer it on the Socrative app, take a look at these 3 balloons and see if you can come up with an explanation for the 3. So, if you've not yet done so, let's get an answer registered here. Maybe about another minute. If you want to look here, here's the top one. Here's the middle one. And here's the bottom one. Okay? So, let's see if you have an explanation for the 3 balloons. Be about 30 more seconds. All right, let's take a look at and see what people have put in for possible explanations. So, different volumes of helium. Well, if it's helium, what do you think would happen to all 3 of them? Then all float. So that doesn't work. Density, what's inside, affects the balloons. That's a possibility. Why would pressure not work?
Because the pressure is the same.
And the pressure is the same. They're pretty much subjected here to atmospheric pressure. If one had a much larger pressure, the balloon would probably wind up bursting or collapsing. Okay, so that doesn't work. The explanation, though, is in terms of the density of the gases. Not the density of the balloons, but again, the density of the gases that are in the balloons. So let's see now what you think might be in the balloons. What do you think could be in the top one? What do you think could be in the top one? Get your answers registered here, please. And count down. 5, 4, 3, 2, 1. Let's go to the second balloon, the middle one. I realize we didn't look at them. We'll go back and look at them after we go through all of them. What do you think could be in the middle balloon? This one here's the middle one. What do you think could be in the middle? Oh, did I not hide those? All right. That's all right. Well, for those of you looking for ideas, right? Okay, get your answers locked in. We'll count down. 5, 4, 3, 2, 1. And then the last one. What do you think could possibly be in this bottom balloon? What do you think could be in this bottom balloon? By the way, these are balloons, just for the record, in case you were thinking there were anything else. They are balloons. All right. All right, let's get your answers locked in, please. Count down. 5, 4, 3, 2, 1. And we're going to start here with the one in the middle. And since that's the one you revealed answers on already, or I did, we'll check it out. And looks like we have oxygen and air. So what I'm going to do here is I'm going to take the one in the middle. And just to make this fun, I think I'm going to inhale some of these gases.
Sounds like a good time.
It does sound like a great time. That's what us chemists do when we have parties. We hang around and we
Inhale gases.
inhale gases, right? So.
Literally huffing gas.
All right, now you see there's not a whole lot interesting going on with this one. Let's just try it one more time. Yeah, see. Not a whole lot going on there. And that's because this one contains,
Like CO2 probably. Not oxygen. CO2.
this one was air. This one was air. All right. So let's go ahead and try the top balloon. So we have hydrogen, helium, helium, helium. I'll tell you that this one is helium. So we'll go ahead. How many ever inhaled helium before? You got to do it just because, right?
Yep.
So now, there's nothing poisonous about inhaling gases, but what does a person always need to be careful of if you inhale a whole bunch? Lightheaded, because what's happening if I'm getting lightheaded?
You're not getting oxygen.
Not getting enough oxygen to the brain. So if I pass out, you have choices to make, all right? And if you're looking at your chest, you might know what those choices are for some reason.
Wow, see? Oh boy, that's really good. Yeah, we, like I say, we sit and pass balloons around. I've been told that when I inhale some of these, sometimes my lips turn blue.
And that's because I'm not getting a whole lot of oxygen to the brain. So I have to be careful that I get enough oxygen to the brain here so I don't wind up passing out. And that's because helium, yeah, we have paramedics on staff here today. Helium, it turns out, if we look at where it's located on the periodic table, over there with the noble gases, the molar mass of helium sits at 4 grams per mole. Whereas when I was inhaling air, air is primarily which gas? It's nitrogen. What is the second most abundant gas in air?
Oxygen.
Oxygen. Shouldn't be a mystery, all right? All right, we need oxygen to breathe, folks. So about 78% of the air by molecules, by molecular count, 78% of them are nitrogen, about 21% are oxygen. The remaining 1% is a mixture, bunch of gases. I've heard some of them already. Carbon dioxide is one.
Argon.
Argon is one. Argon's number 5. Water vapor is number 4. And so then there's a bunch of trace gases that come after that. But if we were to calculate kind of an average molar mass for air, what would the average just consider now, let's think about 75-25, not at 78-21 for nitrogen and oxygen. What would the approximate molar mass of air be? What is the molar mass of nitrogen? Well, be careful now. Remember, nitrogen is one of the elements that is
Diatomic.
diatomic. So it's N2. Oxygen is O2. So what is the approximate molar mass of air? It's about 29, because again, it's about 75% nitrogen and about 21% oxygen by molecule count. So we're now comparing hydrogen to air. Hydrogen, again, a molar mass of about 4, and air, a molar mass of about 29. Which takes us to our next one, and that is which gas is in the bottom balloon. And I see argon, sulfur, a whole bunch of interesting ones, but I see 2 right answers here, 3 of them. And the correct one is sulfur hexafluoride. Sulfur hexafluoride. So go ahead and calculate the molar mass of sulfur hexafluoride. See what you'll end up with. Because this is sulfur hexafluoride. Calculate a molar mass for sulfur hexafluoride. So I'm going to write this information down. We have our gas demo. Helium again is about 4 grams per mole. Air is about 29 grams per mole. Anybody have sulfur hexafluoride yet?
146.7.
Okay, so we'll say about 146 grams per mole. You know, what this is showing here when we look at the balloons, I'll put this one back in here because I don't need that one yet. What this is showing to us is a relationship between the density of the gas and its molar mass. And if we had to talk about the mathematical relationship between density and molar mass, what can we say about their proportionality? Are they a direct proportion or an inverse proportion? Density and molar mass. It's direct. Because as we increase the molar mass, what apparently is happening to its density? It's going up as well. We call it a direct proportion. And so one of the things we're going to be doing here, a whole lot in this chapter, is we're going to be talking about proportionality. And in fact, this is the first time of just about every chapter from here on out we'll be talking about proportionality. So you need to know what it means. So if we talk about something that is a direct proportion, direct proportion means if we double one variable, then the other one will double as well. If we cut it by a factor of 10, the other one will be cut by a factor of 10 as well. That's called a direct proportion. So if we then have variables that are inversely proportional, that means if we double one, the other one gets halved. Or if we cut one by a factor of 10, that means the other one will increase by a factor of 10. So again, those are inverse proportions and direct proportions. And here's the way we show it. If we want to talk about density and molar mass, we say that the density is directly proportional to the molar mass. And your text abbreviates it with some sort of script M. I'm going to write molar mass like this. And so when you see this symbol right here, when you see this symbol, that symbol means is proportional to, or is directly proportional to, actually. So what they were saying then is the density is directly proportional to the molar mass. And if we talk about pressure and volume, and we'll do this one just real quick. Pressure and volume. Here, take my syringe. So start with a syringe like this, and our paramedics waiting, by the way, for the sulfur hexafluoride. So we'll just, it'll be about 5 minutes. Okay. So we're going to, well, you know our paramedic. This is Neha, right? You all met her in lab? Yeah? No? Yeah. All right. Paramedic, hopefully we're not stretching it too much, are we? Okay. All right. So, good. All right. So now, what we're going to do with this is we're going to increase the pressure of this gas, and if I increase the pressure of the gas, what's happening to its volume? Decreasing. If I decrease the pressure, what's happening to its volume? Increasing. This would be a inverse proportion. So if we double the pressure, the volume gets Have. Okay, now if we want to show that, here's how we do this. We say that the pressure is inversely proportional to the volume. That's the way we show an inverse proportion. So we read the first one as density is directly proportional to the molar mass. The second one we read, the pressure is inversely proportional to the volume.
Can you also like reverse the symbol?
Depends upon which one you want to say is the dependent variable.
No, like the symbol in the middle.
Oh, the symbol? No. No, it's not. It's not like a less than or greater than symbol. So we always show it. This is like the Greek letter alpha. Okay. So we come back now. Of course, that's not what you're really wanting to know. You want to know what happens when you inhale it, right? So that's what you're all waiting for. So what we're going to do here is we're going to inhale some. What do you think is going to happen? You think so? Luke, I am your father? Okay. Luke, I am your father. Star Wars, right?
Yeah.
Okay.
He never actually says that though.
I need a scissors here. Scissors. All right. Now, before I inhale this, you might think, gosh, this guy's crazy. Because after all, now that's what I thought the first time I saw this. And the first time I saw this was back when David Letterman was not, well, I think they just probably started his own show. I don't actually remember. It was back in the middle 90s, so I think he had his own show at that point. And they talked about this guy who was going to inhale sulfur hexafluoride, and I thought, this is really crazy because sulfur, if you ever smelled sulfur, nasty smell, right? And then fluorine, this is like the most reactive of all the non-metals. And so if you take like the nastiest smelling compound in the world, or the nastiest smelling element, and combine it with this really poisonous gas, certainly you can't inhale this stuff, and he did. So I went back, and of course this was in the days before the internet, or at least not very wide use, and I went and looked through some MSDS information on sulfur hexafluoride, and I found out that it's actually a rather chemically inert compound. In fact, I had some students that very first year that I demoed this say that they worked with sulfur hexafluoride. And any of you happen to work with it already? Okay, but it was a place in Anoka here where they were welding electrical components, and they used sulfur hexafluoride as a gas to provide an inert atmosphere when you're welding components, so there's no corrosion or whatever around the tips. And so as I read about it a little bit more, basically the biggest caution is that you don't want to asphyxiate yourself. But that's the same thing with the helium, is you don't want to asphyxiate yourself. The difference, though, is that when you inhale the sulfur hexafluoride, where's it going to go?
In the bottom of your lungs.
It's going to go into your lungs. And when I open my mouth, where's it going to go?
It's going to stay in your lungs.
It's going to stay in your lungs. Whereas if I inhale helium, I open my mouth, where's it going to go? It'll go out. So that's the main difference between this one, even though it's relatively chemically inert, is that because it is dense, I do have to be a little bit more careful in its use. So, what was it? Luke, you are my... Luke, I am your father.
Now, this is a lot of fun to do, and like you gotta be really cool. Wow, yeah, see, that's really cool though when it does that.
And
sometimes I need to be careful when I take a hit of this stuff because, you know, you gotta make sure that you get some oxygen in, so breathing is quite important. Well, I can't guarantee I'm not sick. I haven't been sick, but, you know, we got a little bit left here if anybody wants to take a shot. I know you did ask about the first, so if you want to take a shot of this, you can. But one of the things that you got to do to get rid of this stuff is
Bend over or lay down.
Am I normal yet?
no, you got to inhale something. Well, what you at least need to do, if you want to make sure you get rid of it, is just bend over and make sure then that the more dense gas is able to escape from your mouth. All right, so we'll take this back here. Now, one of the things I should mention here, and one of the reasons why I was checking to see if the sound worked. And this balloon is filled with an extremely dense gas called sulfur hexafluoride. Now, sulfur hexafluoride has a density which is 5 times greater than air. In other words, its molecules are 5 times heavier than corresponding air molecules. And they also happen to be, in case you're interested, about 35 times heavier than molecules of helium. So let's just see what these heavy molecules do when I inhale these.
Okay, and as you can tell, my voice gets really low. And the interesting about the sulfur hexafluoride is that because it is so dense, the sulfur hexafluoride stays down in my lungs, and as such, I can talk much, much longer with a deep voice because that sulfur hexafluoride has gone down into my lungs and is staying there. Now, I'll take just one more swig of this sulfur hexafluoride so you can just really tell how this works. Oh, boy. Oh, I almost threw up on that one. So, the molecules are so heavy. Now, the thing I got to do here is that before I go out and run a marathon, I got to purge my lungs of this stuff. The way I do that is stand on my head. So, Niels, you care to give this a shot? So, oh, I think I got rid of it.
When your voice is raising in pitch, you sound kind of like Kermit the Frog.
Okay. Well, there's all sorts of interesting comments there. If you want to read through there, this one I had to share because it went viral before a couple different times. And didn't you know Ray Williams Johnson? Yeah. So I was featured on there one time. And I will link that to the D2L course here later today if you want to see those articles. All right, so that's it here for the little introduction. Any questions on our little intro to gases? All right. So that was 1994. Yeah, so I mean, I look at my life and it's like, wow, it's a long time ago. But it was on YouTube. YouTube didn't exist then. I uploaded this about 9 or 10 years ago. And YouTube was just starting, yes. All right, so let's see, where are we? Let's talk about gas pressure. Let's talk about gas pressure. And to talk about gas pressure, I'm going to do another demo here. I'm going to set this aside, and we're going to put everything into this bucket. I'm going to go and get the explosion screen. So all I'm doing here is I'm just filling this up with room temperature water. And this is one of the demos that you can do at home. And I'm going to go ahead and get out the Bunsen burner. And what I'm going to do now is I'm going to take a couple of pop cans and I'm going to heat them up. And then we're going to watch what happens to their behavior. All right, we have this, and I need some tongs here somewhere, which I know I have on my cart. we'll go ahead and get this started. And the first thing we're going to do is we're going to take an empty pop can, and I'm going to heat it up until it gets smoking hot, and then I'm going to invert it into this bucket of water, or this beaker of water. And so again, the key here is to heat it up till it gets smoking hot. And again, this is just air. It's been sitting here under my desk for several months. I save it up for this demo specifically. And again, we're going to heat it until it gets smoking hot. Once it's smoking hot, we invert it in here. We see not a whole lot interesting happens to this one. On the second one, what we're going to do is, you see that this one is empty, but I'm going to add just a small amount of water to it. So you can hear that we just have a small amount in the bottom. Now what I'm going to do this time is again heat it up till it gets smoking hot. In terms of the amount of time it takes, is it going to take more time or less time to get it smoking hot? A little more, because I have to also heat up the water till it begins to boil. Now in order to have success with this one, it does have to get smoking hot, and you do have to hear the water begin to boil in the bottom. And you want to heat it long enough such that the water inside of there vaporizes and turns from liquid water into gaseous water. Okay? So now, once we've done that, of course, there has to be some sort of explanation for that. So, why did the pop can containing the vaporized water collapse when inverted into the beaker of water? Why do you think the pop can collapsed when it was inverted into the beaker of water? You can always feel free to talk to the neighbor. If you're not sure, you want to sound semi-smart when you write your answer up. Okay, you're getting a handout here. Once you get the handout, these funky looking figures are supposed to be folded there. It's supposed to be the front page of the booklet. Okay? So these funky looking figures are supposed to be the front page of the booklet. They're hot off the press. Let's see, we got 16 people locked in. Let's get your answers locked in here, please. And we're going to count down 5, 4, 3, 2, 1. No idea. Drop in temp. Water. Because when inverted the water, the gaseous water vapor built up in the pop can and caused the pressure. Okay. Pressure on the outside of the can is greater than on the inside of the heated can. Right here. What it is. The pressure on the outside of the can was greater than the inside. That is correct. Now, how did the pressure on the outside become greater than the inside? Why do you think that happened?
The gas on the inside.
Right, on the gas on the inside, because remember, the gas actually didn't just cool down. Remember, the key to success on this one was converting the liquid water into gaseous water. So when I invert it back into the beaker, that gaseous water does what? Condenses back into a liquid. Once it condenses back into liquid, the inside of this can is basically a vacuum. And all the pressure that's acting in the can is all acting on the outside of the can. So again, the key to this one is the fact that we had to vaporize the water by inverting it into the water. That causes the water inside to condense. Once it condenses, that creates a vacuum. All the pressure acting is on the outside. And that's when we talk about gas pressure, your understanding of gases in this chapter will come down to this. We say that gas pressure is caused by collisions of gas molecules with surfaces. And just to show you that this first can that we looked at, there's nothing magical about it. We have a little bit of water still in here. All we need to do with this one is to come back and heat it up with my tongs. Here we go. So if I come back here and heat this up, again, the key to success is what? Right, we have to vaporize the water into a gas. So basically create steam. And if we can hear the water boiling in there, that means that that water vapor is displacing the air that's in the can. Popping it in here, that can winds up collapsing. And to give you an idea of how much pressure that is, this is something that my uncle made for me before he died. And this is a bar made of iron. This measures 1 inch by 1 inch, and it has a weight of 14.7 pounds. And so if I set this here on the floor, or if somebody put out your hand here, we'll turn it this way and set it on your desk. I'll try not to have it bear the whole weight, but it's starting to get heavy. Yeah, very heavy. Yeah. And so if I'm pressing down with this, this is 14.7 pounds per square inch. This is actually equal to 1 atmosphere of pressure. Okay, so this is how much pressure is acting on every square inch of your body. If you now can imagine taking this here and putting it on every square inch of your body, there's 14.7 pounds per square inch that's acting on your body right now. And that's why this pop can collapses, because acting on every square inch on the outside of this can is 14.7 pounds. Now actually that varies a little bit with atmospheric conditions. Here in Coon Rapids it's probably more like about 14.4 pounds per square inch. It's going to be 14.7 pounds per square inch if we are at sea level on an average day. So even at sea level the pressure is going to vary a whole lot. If you pay any attention to like the weather here, the last month or so when we've had all these hurricanes, they have low barometric pressure, and when you have low barometric pressure, then there's not as many molecules or whatever that are in the air at the time to cause those collisions. Yes?
Would you care to clarify how sea level is determined?
I'm not going
in relation to land masses and stuff?
I don't know what your question is.
Like, the mass of a mountain would pull the water up, so would sea level be determined by the mass of the land that's there? Or is it just a static sphere around the planet?
I'm not sure really what you're asking.
Does sea level vary, or is it just a perfect sphere?
Well, sea level is going to vary based on the gravitational attraction of the moon, for example. So, I mean, it's not going to be a perfect sphere, and the Earth itself is not a perfect sphere. So, if we got rid of all external gravitational influences, which we can't do, I mean, we got the sun and everything else, yes, then we maybe could, in the absence of any other acting forces, but we don't have that absence here at all. So, all right. So when we talk about the gas pressure being caused by collisions of gas molecules with surfaces, we are going to be using some units to measure the gas pressure. And those pressures, like we mentioned, one of them is pounds per square inch. We might write it like this. So we might write pounds per square inch. But we can also write it as PSI. And it turns out that the ordinary atmospheric pressure exerts a pressure of about 14.7 pounds per square inch, or we write 14.7 PSI. The other thing we can say about this pressure, and Alex mentioned this already, this pressure is also called 1 atmosphere. This is 1 atmosphere of pressure. And it's probably going to be the most common units that we use. We say that 1 atmosphere is equal to 1 ATM. And so 1 ATM is equal to 14.7 pounds per square inch. Now if you open up your, or pull out your periodic table, you can go to the flip side and you'll see a list of conversions here. There's a whole bunch of pressure conversions that are listed under here. And of course you're always going to have this list of conversions available to you. Yes?
Can that ATM withdraw money from my bank account?
Anybody need a fresh copy of the periodic table or conversions? There's one. Pass this one down. Anybody else? Okay, anybody else? All right, so you can see there's a number of other units that are used. You do not need to memorize these conversions because these conversions will always be available for you to use. One of the things I'm going to point out here, though, is that the SI unit of pressure is the Pascal. So this unit right here, the Pascal, is the SI unit of pressure. Now the way that we abbreviate the how should I say it? Or the way we calculate the pressure is like this. We say that the pressure is equal to force over area. Pressure is equal to force over area. And if we put that in symbols, we say that P is equal to F over A. So now, if I were to bring this wood block out here, and what I'm going to do is I'm going to stand this wood block up in a number of different orientations. I'm trying to remember which one I had as the right choice. So this is orientation A, right here. This is orientation B. This is orientation C. So look at it again. Here's orientation A. Here's B. Here's C. Which orientation would exert the greatest pressure on the surface of the bench? Is it A? Is it B? Is it C? And feel free to talk with a neighbor. Is it A, B, or C? A, B, or C? One more time. A, B, or C? Which one exerts the greatest pressure on the surface of the bench? Give you 10 seconds. A, B, or C? And we'll count down. 5, 4, 3, 2, 1. Correct choice is A. And why is A the correct choice?
Because it minimizes the area.
Smallest area, right? It's the smallest area because all of them have the same force. The force comes from the weight, from the gravity, right? And so I haven't changed the weight, but what I am changing is the area that's in contact with the surface. So if I make the area smaller, that makes the pressure greater. What do we call that mathematical relationship? Inverse proportion, right? It's an inverse proportion. So let's write an inverse proportion that shows the relationship between pressure and area. We would say P And then what? 1 over A, right. So if we want to show an inverse proportion, we'd say that the pressure is proportional to 1 over A, which is the same as saying that force and pressure and area are inversely proportional to each other. Let's come back here. I think that was the next question on the Socrative app. Was, yeah, pressure and area are inversely proportional to each other. Let's go to the next one. How about pressure and force? Looking at this mathematical equation. According to this equation, pressure and force are related how to each other? And you can tell simply by looking at the equation. So we'll count down on this one. 5, 4, 3, 2, 1. These are direct proportion. And how can we tell simply by looking at this equation?
Force is on the top.
Force is on the top. If we double the force, what happens to the pressure? It's going to double as well, because both of them appear in the numerator. So if you double one, you must double the other. This is a direct proportion. If we go back to this one here, this is an inverse proportion because pressure here appears in the numerator, while area appears in the denominator. If we have a bigger area is going to make a pressure that is smaller. Okay. Area bigger, pressure is going to be smaller, and so that then is an inverse proportion. All right. So any questions on that piece there? Okay, if we check out the units on pressure, we said that the SI units of pressure were the Pascal. So if we want to look at how that's calculated, we say that pressure is equal to force over area. Let's go ahead and figure out what the units of force are. Now, if you've had some physics, how do you calculate force? Mass times acceleration. Exactly, mass times acceleration. What are the SI units of mass? Kilograms. And for acceleration, what are the SI units of acceleration? Meters per second per second, which is meters per second squared. So this would be the units on force. So now, if we go ahead and plug that into this equation, say it's a kilogram dot meter per second squared, and then we divide this by the area, what are the units of area? Meters squared. Okay, so we're taking kilogram dot meters per second squared and dividing that by meters squared. So when we divide by a value, dividing by the value is the same as multiplying by its reciprocal. So it looks something like this. Then what's going to happen is that meters will cancel out with one of these here, and it looks like we wind up with units of kilograms per meter dot second squared as being the units of pressure. And if we have a 1 kilogram per meter dot second squared, this here is equal to a unit of pressure called a Pascal, and we abbreviate a Pascal with capital P and a lowercase a. And so again, this right here, this is the SI unit of pressure. Now, something else that we should go through. I forgot to copy this onto your sheet, but this is a diagram of a mercury barometer. And who pays attention to barometers in general? Right, the weatherman, the meteorologist, if we want to be gender neutral. So the meteorologist. Would talk about it because what we want to do is we want to find out what the effect is of the atmosphere on the weather. Or actually, we can look at the pressure and determine what's happening. So the way that a barometer is designed is like this. Basically, it takes a pool of mercury, and into that pool of mercury, we take a tube that has been evacuated. In other words, it has a vacuum. And once we place it, and just like if you had a straw drawing the liquid up, sucking the liquid up, you create a vacuum, the liquid goes up in the straw, and the reason why the liquid goes up in the straw is because the atmosphere is pushing down on the surface of the liquid. Yes?
Fun fact, at about 0.8 atmospheres of pressure, a normal human can pull about 22 inches of mercury.
That's probably true. Yeah, that's probably true. So if we were to look at the pool of mercury, the mercury is going to go up inside of the column here, and on average that height is going to be 760 millimeters. And that 760 millimeters of mercury, if you come back to our list of conversions, we see right here that 760 millimeters of mercury represents the height of a column of mercury inside that evacuated tube. In other words, it's the difference in height from this pool surface up to this level. Now, any idea why mercury is used as a standard? That's a liquid. We could actually, there's such a thing as a water barometer. Well, the reason why is because the most dense liquid we know of is mercury. And so, because it's the most dense, it's going to produce the column that is the shortest. Okay, we could use water. If we use water, we could draw water up about 30 feet. Okay? If you had a straw that was 31 feet long, you would not be able to draw water up a 31-foot long straw. But if it was 30 feet and you could create a perfect vacuum with your lungs, then you could draw water up about 30 feet up inside of a straw. So again, it just depends upon what the liquid is. Mercury is chosen simply because it is the most dense of the liquids. And then what we do, when you watch the weather forecast, of course, they don't talk about it being in millimeters of mercury. You'll hear it be described in inches. And so you might hear that the barometric pressure is 29.35 inches. And what that's talking, if it's 29.35 inches, is that would be the height from the pool up to the surface. And 29.35 inches would actually be a case of low pressure, because it's actually less than it is on average at sea level. And if it would exceed 29.92 inches, then we'd have a relative condition of high pressure. And we do more to it than that. I mean, when you hear the weather, the barometric pressure given on a forecast, it's always been corrected to 0 degrees Celsius and sea level. But again, at sea level, on the average, that height would be 760 millimeters. And that's at 0 degrees Celsius, it turns out. Okay, any questions on this piece? All right, so let's go to figure here in your handout. This figure right here is a manometer. And specifically, this is, we want to cross these out because this has answers, right? I don't think yours does. All right, so this here is what's called a manometer. And a manometer is a device that can be used to measure the pressure of gases. And there's two different types of manometers. There's what's called closed-end manometers and open-end manometers. And you take a look at the end of the manometer here to determine whether it's an open end or closed end. And what does it look like to you? This is an open end manometer. Okay, this is an open end manometer because it's open to the atmosphere. And in this particular example, we'll write this down as an open-ended manometer, or an open-end manometer. What we can do is we can figure out what the pressure is of the gas inside of here. So what we'd like to know is, what is the pressure of the gas? And so we use subscripts to indicate which pressure we're looking at. So in each of these cases, we want to know the pressure of the gas. So if we go to the first one, we take a look at the mercury levels inside of here, and we see that it's like this. Can we see that the pressure of the gas inside of here is greater than or less than the atmosphere? Greater than. Why? It's pushing this down further than the air or the atmosphere is pushing it. If we look in the second one, the pressure of the gas is less than the pressure of the atmosphere because the atmosphere is pressing this level down a little bit further. So the first conclusion we could make in here is we could say in the first one the pressure of the gas is greater than the atmosphere. And so if we want to show atmosphere, we usually abbreviate ATM. And the second one would say that the pressure of the gas is less than the atmosphere. Then we should be able to figure out the actual pressure of the gas if we knew the pressure acting on that, acting by the atmosphere. And so let's assume an atmospheric pressure of 750 millimeters of mercury. So let's assume an atmospheric pressure of 750 millimeters of mercury. If that's the case, then we'd like to know what is the pressure of the gas. We'd like to know what is the pressure of the gas. So we can first of all begin by saying, without doing any calculations whatsoever, we said that the pressure of the gas is greater than the pressure of the atmosphere, so we can say that the pressure of the gas is more than 750. How much more?
45 millimeters of mercury.
45 millimeters of mercury more is what it is. So what do you think we do to calculate the pressure of the gas in this case? Add them together. It's that simple. This is the simplest math we're going to do all semester. Okay? We simply add these together. We would say that we wind up with 795 millimeters of mercury for the pressure of the gas. How about the second one?
You subtract 25 millimeters of mercury.
Right. And we subtract 24 in this case because this is the difference in height between the two. And what do we subtract the 24 from? Right, 750, because that's the assumption we're making. I just made up the 750. I could have made up 760 or 721. I could have made up any numbers. In this case, though, we're subtracting from the atmospheric pressure. We wind up with 726 millimeters of mercury for the pressure of the gas in this second one. So gas pressure is very simple to deal with. Any questions on the first one? Okay, then let's open up our packets to the next page. The next page, we already did a demo with this one. I think that's the first one here. So pressure and volume. We want to look at the do a pressure versus volume. We're going to make some abbreviations here. P is going to stand for pressure. V is for volume. Temperature would be T. And number of moles would be N. Okay, so if you want your abbreviations, again, P is pressure, V is volume, T is temperature, and N is moles. So let's look at the first one here. In your graph, we want to do P versus volume. So in P versus volume, this means we're going to deal with constant temperature and constant, what else is going to be constant? Number of moles, so it's going to be constant N. So if we do this, we go ahead and press down on this gas, what happens to the volume? Does the volume increase or decrease when I increase the pressure? It decreased. So what is the relationship? Inverse. If I release the pressure, decrease it, what happens to the volume? It increases. So let's go ahead and write down some information associated with this. Where's my stylus? Doesn't matter. Here we go. All right, first one. We want to say that the relationship is P is Is it directly or inversely proportional again? Inverse. So we say that P is 1 over V. There we go. Then what this means is that PV is equal to a constant. So P times V is equal to constant. Another way of saying if P times V is equal to constant is we could say that P1 times V1 is equal to P2 times V2. Where subscript to 1 means initial conditions, subscript to 2 means final conditions. Okay? Now if we plotted this, here's your graph right here. If we put P and V over here, what does a graph of an inverse proportion look like? Is it like this? Is it like this? Is it like this? Well, think about it now. I know you've done this in your math classes. Let's say we want to plot x, y is equal to 4. What does the graph look like in the first quadrant? It's a curve. It's called a hyperbola. It's called a hyperbola. And if you're doing x, y is equal to 4, you're going to have a graph here. And you basically have its reflection in quadrant number 3 down here, right? Okay, but we don't have negative pressures. We don't have negative volumes. So we only look at the first quadrant. Your graph of an inverse proportion is going to look something like this. And of course, I'm not a very good drawer, but it's going to wind up approaching the axis without actually ever quite touching it. And again, the shape of that graph is called a hyperbola. It's called a hyperbola. The name of this is called Boyle's Law. Boyle's Law. Second one. I need to go and grab my stuff because I forgot to bring it in. Next one, though, you can label it. It's going to be constant P and constant N. So if we want to show this, what we're going to do, we're going to use a balloon to demonstrate this. And put this balloon in here. And somewhere, I thought I had a I don't know where I put that. Well, we'll do this. We will dump this water out. Sorry about that. I heard it's like a Shamu show up here sometimes. All right. Anybody know what this is? Liquid nitrogen. There's a liquid nitrogen here. And what I'm going to do is I'm going to pour some liquid nitrogen. Now what do you think is going to happen to the balloon? Okay. That's kind of cold. Forgot to warn you guys. Okay. There we go. So, if I now asked you, what is the relationship between the volume and the temperature? It's a direct proportion, because as we decrease the temperature, we decrease the volume. So, if we want to show this on a graph, let's go ahead and do that. First of all, we need some symbols here. Constant P and constant N. So, P is constant, N is constant. And let's see, what is our next one? V versus T. So we want to show a symbol here. If we put V here, what should we do on the other side of it?
D.
Put a T, right. This again is a what type of proportion? Direct proportion. What this tells us is that V over T is a constant. V over T is a constant. And what that means is that if they're a direct proportion, if we cut V in half, then T must be in half. And if we cut each one in half, that remains a constant value. That's what this is saying. Now, if we want to show it with subscripts in initial and final conditions, we'd say V1 over T1 is equal to V2 over T2. The name of this, by the way, is Charles' Law. Did we name the first one? Boyle's Law. There we go, we did. So then if we had to plot this, if V is here and T is here, what does a direct proportion look like? Straight line starting where? At the origin, exactly. Straight line is what a direct proportion looks like. By the way, if we take this out of here, we can go ahead and let that warm up. And we see, of course, as we increase the temperature, what's happening to the volume? Increasing as well. Okay, next one. Where's my next device? Next one, we are going to look at pressure and temperature. Pressure and temperature. So in this one, it's going to be constant V and constant N. So now I'm going to cool this one down, and I also want to warm it up, so I'm going to start up my burner again. Alright, we have a pressure gauge here. Look where the pressure is, it's sitting right around 15, and of course that's in units of pounds per square inch. As I cool it, what's happening to the pressure inside of here? Going down? Yeah. Okay. If I heat it up, what's going to happen to the pressure? Should go up. Is it going up? Yeah, okay. All right. So, what is this mathematical relation? A direct proportion. Let's write down our relationships. What is our first one? What are symbols we use? P proportional to T. Another way of saying this would be P over T is a constant. Using initial and final, we could say is equal to P2 over T2. And if we were to graph pressure and temperature, what do we get? Straight line out of the origin, looking something like this. And this does have a name. We don't use it very common. This is often called Gay-Lussac's law. Now this one is not on your sheet. I forgot to add it on. But let's say that we had one where we had a constant P and constant V. No, not constant V, constant T. There we go. And now we want to do a number of moles versus volume. So speculate now, without me even telling you or making an observation, is it going to be a direct proportion or inverse proportion? What would the equations look like? And what would the graph look like? So reason this out. The pressure's constant and the temperature's constant. We're running a little short on time here, so I'll help you out. Direct or inverse? Should be direct. I mean, one of the ways I just demonstrated was I blew up a balloon, right? If I put more moles of a gas in, what happened to the size of the balloon? Got bigger. So that proportion again is a direct proportion. We would say N1, what is that? N1 over V1 is equal to N2 over V2, which means that N over V is a constant, and the graph of N versus V is going to be straight line up out of the origin. Okay, we got like about 3 minutes left here. I can't bring out liquid nitrogen without playing with it a bit. Temperature of liquid nitrogen is minus 196 Celsius, which is minus 359 Fahrenheit. So very cold. One of the things I can do with this is I have a piece of rubber hose right here. And if I take this rubber hose and put it into liquid nitrogen, watch what happens now when I drop it in. Now listen what happens as well. Now do you hear what's happening when I drop it in? It begins to boil. And so when it's boiling, it's turning from a liquid into a gas. And that conversion of liquid into a gas, because the tube is warm, basically forces the liquid out the end. But now if I let this sit in here for a while, what's eventually going to happen to this hose? It'll freeze. You're listening inside of here. You'll hear that the boiling is basically coming to a stop. A little bit of nitrogen coming out yet. Okay. And now we have a piece of hose, which, if I were to come back here just a bit, you can see that it becomes very brittle. Okay? Now, something else we can do with this that's kind of cool, and I don't know where I put all the rest of my demo stuff here today. I'm hoping there's no cracks in this. But what I'm going to do is I'll put a little bit of water in here. And yes. Oh, no questions? We can go ahead and pour some liquid nitrogen onto this. And if you see the liquid nitrogen, where is it sitting? On the top. Which tells you that it is less dense than water. Another kind of cool thing with this, and I'll let you do this before you leave today because we are running out of time, but listen to my hand. Okay? Now I can stick my hand into the liquid nitrogen and not freeze it, because what's happening to it as I thrust it in? It's boiling, and at least for a short moment, it's causing a vapor barrier between my hand and the liquid nitrogen. Now if I left it in there, of course, it's going to do this, right? And the last thing I'm going to do here before you're going to get a chance is you can lift up your feet and your backpacks and whatever else. I'm going to do a cleaning job for the maintenance staff here. And when I pour the liquid nitrogen out, the liquid nitrogen will form little balls which will go rolling out to the walls, and as it goes flying past you, look at those little balls. You're going to see dust balls beginning to form, and we're going to be pushing all the dust to the walls. Alright. And on your way out the door, if you want to come in here, There's not a whole lot left, but you want to stick your hand in liquid nitrogen, feel free. That's it for today.